Partial stroke testing is a type of diagnostic function, and we measure the ability of a diagnostic function to detect failures by something called its diagnostic coverage factor. So the purpose of today's presentation is to give a little bit more background on how to use the FMEDA, or Failure Modes, Effects, and Diagnostics Analysis Technique, to try to determine what effectiveness you should assign to a partial stroke test. And that effectiveness is going to be a function of the type of valve that you're using and the service that it's in. And hopefully you'll be able to get some historical data to help you make that determination. And a little bit later on in the presentation, I'll talk about some of the sources that you can use, that we have used in the past, to obtain that information. So first off, what exactly do I mean by a partial stroke test? A partial stroke test is a periodic command to move a valve a small amount. Partial stroke tests typically occur on shut-off valves that are normally open, and you send the command to close the valve maybe 5 to 10, 15, maybe even 20%, depending on what the service is and what the impact of stroking the valve is in terms of upsetting the process. It is also possible to do partial stroke testing on valves that are normally in their closed state and fail open, or open to achieve the safe state. Typically that's going to require a special type of valve where you can move the valve stem a certain distance without actually opening the pathway for liquid to move. That's more of a specialty item. So when we send that periodic command for the valve to move, we're going to try to detect that motion has occurred. And once we are able to ascertain that either motion has occurred or it's not going to occur, which is another important factor that you need to consider, we're going to send the valve back to its original position. The value of doing this type of test is that the process stays in operation the entire time that the test is occurring. So you're not going to upset your plant, you don't need to stop operations, and you don't need to have any elaborate bypassing mechanism that's going to allow you to run the test while the plant's in operation. And depending on what the service of the valve is, what type of valve, you can achieve a 60% or greater diagnostic coverage. And again, what I mean by a diagnostic coverage, and we'll get into more detail a few slides from now, is what is the fraction of the overall dangerous undetected failure rate that you would be able to diagnose when this type of with this type of event occurring. Okay, moving on to the next slide. The approach that we're going to use to calculate that diagnostic coverage is something called FMEDA, Failure Modes, Effects, and Diagnostics Analysis. This is something that we're going to do for a multi-component system, and in that system, we're going to systematically analyze every component in the system, looking at all of the failure characteristics of each component, and one at a time assessing how the entire system would respond to each different failure mode of each component. Okay, what I'll start out with is a quick example of the FMEDA approach. And the example that I'm giving you is using a multiple temperature transmitter configuration to measure a differential temperature, for instance. So in this case, I have 4 components in my system, 2 temperature transmitters upstream and downstream, and a thermocouple for each of those transmitters, and the overall functionality of those 4 components is to calculate the probability or the likelihood of failure of the overall differential temperature measurement. Okay, so looking here, the first item on the spreadsheet, and I will give you a little bit more information on some spreadsheet tools that you can use, is going to be the component name. So each component is going to have its own identifier. That happens in this row. So there's going to be temperature transmitters and thermocouples. Each has a unique identifier. The next row over, we would have a generic type of device. So in this case, we have transmitters and thermocouples. Okay, the next thing that we're going to do is we're going to list the modes of failure for each of the different types of devices. So for a temperature transmitter, the modes of failure, a simplified list of modes of failure, are that it can either fail upscale, high, it can fail downscale, low, or it can fail what we call dangerous undetected, which means it's essentially failed in place. Okay, so that's the modes for the temperature transmitters. And for the thermocouples, again, you can fail low, which is by far the most likely situation to occur, or you can fail high, or again, you can fail dangerous undetected. The next step would be for each failure mode, you need to determine how that failure affects the overall system. So if the first temperature transmitter in a differential temperature measurement fails high, is that an initiating or an inhibiting failure? So the next column over the effect, we're going to say initiating and inhibiting. And that terminology is a little bit more obscure than what would more commonly be used would be a safe failure or a dangerous failure. And an initiating failure, as we discussed previously in the training class, is a nuisance failure or a safe failure, and something that inhibits is a dangerous failure or a covert failure. Okay, after we list out all of the failure modes and whether they're safe or dangerous, we're going to quantify them. And in this case, something that I didn't talk about a lot in the training class is we use failure units, or FITs, which the most common measure that we used was 10 to the minus 6, or failures per million hours. A FIT is 1 failure per billion hours, or times 10 to the minus 9 in terms of failure rate. So what we did was for each of the failure modes, gave it a failure rate. So the top row was temperature transmitter failing high. We went into our database and determined that that was 150 FITs, or 0.15 failures per million hours. And we also determined that that failure was dangerous, it was inhibiting, so we take that 150 and we put it in the dangerous column. Conversely, there's 750 FITs for safe failures, and then we put that in the safe column. So for the rest of the components and the rest of the failure modes, we'd list what is the overall failure rate and assign that failure rate into a column. The next step would be quantifying the diagnostics. So we would look at each failure mode and determine yes or no, is this failure detectable? And if so, we would put a note in as to how it is detectable. So for instance, the top row, again, was a transmitter failing off scale high. Well, that is detectable. All we need to do is program our PLC to detect that the millivolt or the milliamp input to that I/O channel is significantly in excess of 20 milliamps. How much in excess of 20 milliamps is going to be a function of which equipment vendor we're talking about. But in general, we just call that a PLC over range, and a lot of PLCs have this built in automatically. It just simply generates a bad PV. So since that is detectable, we put a 1 in the detectability column. We put in a note on what exactly the diagnostic is, in this case PLC over range. And then the spreadsheet that we use actually, if we put a 1 in for detectable, it will then carry over the failure rate from the previous column where we said what is the dangerous failure rate. Since it is detectable, we will transfer that number over to the detectable column. So you'll see that on this spreadsheet, most of the failures here are detectable except for these 4, and the description on these is essentially you're stuck in place or a dangerous undetected failure. For that, there is no diagnostic, and because we put a 0 here, there's no failure rate carried over into the covered column. Okay, and then finally, all we do is after we perform this systematic process for each component and each failure mode, you carry everything down to the bottom. So we took the failure rate column, added up all the numbers to come up with a total failure rate, 13,000 fits, or 1.3 times 10 to the minus 5 failures per hour. We added up all of the dangerous failures, all of the safe failures. We added up all of the dangerous failures that are detected, this would be safe detected, and all the dangerous failures that are detected, or detectable technically. Based on those numbers, we can do some ratios to come up with the numbers that we use to quantify the system. Things like the percent safe failures, which is just simply is it safe or is it dangerous. The safe failure fraction, which we described, is a little bit more elaborate, that includes not only the inherently safe failures, but also the dangerous detected, in this case 87%. And then we calculated the coverage. The important thing to remember for the coverage, or how we calculate the coverage, is we look at what is the failure rate of all of those failures that are detectable, in this case 5650, divide that by the total dangerous failure rate, which in this case was 7350 fits, and that ratio came to 77%. So that's how we calculated the coverage of dangerous failures. Now, everything that I just showed you in this spreadsheet, we have the same spreadsheet that I used to do this example available on our website if you want to go download it. The URL is going to be kenexis.com, resources, documenttools.aspx, and while you're there, there's at least 7 or 8 other document tools that you might be interested in downloading too, things on bypassing, variety of other items. Okay, so now that I've explained how we do an FMEDA in general, let's look at valves specifically, and specifically the problem of partial stroke testing. Okay, if you have a valve, and I'm just showing an example of a quarter turn valve with a piston type actuator, the valve can fail in a safe state or an initiating state in several ways. And for this example, we're looking at a valve that's open under normal conditions and closes on demand. So this is a shutoff valve as opposed to like a blowdown valve, which would be the opposite. Okay? So if a safe failure occurs, the result is that the valve is going to move to the closed position when it was not commanded to do so. Well, what are some of the failure modes that are going to cause that to happen? Well, we could lose our instrument air supply. That's going to cause the spring to force the valve closed. Or we can get some severe leakage of the piston seal, which is also going to allow the spring to force the valve to go closed. Those are the examples of the safe failures. For the dangerous failures, again, the valve is in the same service, but now what we're looking at in terms of result is that the valve the valve is commanded to close, but it either does not close or there is significant leakage. In that case, the valve failed to perform its safety function. Well, now how can this occur? Well, there are a number of reasons. You can have the piston jamming on the cylinder and not moving after you let the air out. You can have a clogged inlet or outlet for your pneumatic system, causing basically the air not to bleed off. You can have a broken spring that will prevent the spring action is what you're requiring to cause the valve to go to the safe position. If the spring is broken, it will not work. You can have the valve stem jammed, or the valve stem can be broken off altogether, so the actuator can turn it all at once, but the ball is not going to move. You can have the valve ball jammed against the seat, or you can have the valve ball jammed against an obstruction. Some of my favorites would be welding slag, welding rods, Coke cans, hard hats, you name it. I've heard about it being stuck inside of a valve. Another failure mode that can't be forgotten is erosion or corrosion causing significant leakage even when the valve is in the closed position. Now, that gave you the full range of failures that can occur. So let's talk about, well, what would we do with that FMEDA spreadsheet? Well, let's look at the overall system. So for a shutoff valve, the system I would say would be the solenoid valve, the actuator, and the valve itself. And for each one of these, there are going to be failure modes. So for the solenoid, I can have a short in the coil. That's going to be inhibiting. That's going to prevent the solenoid from de-energizing, which prevents your system from working. You can have an open circuit in the coil, which is going to be a safe failure. That's going to cause everything to go to the safe state. Your SOV plug or your plunger can spuriously move, which would be safe, or it could get stuck, and that would be a dangerous failure. Similarly, the other failure modes that we're concerned with in the actuator: loss of air, seal leakage, jammed cylinder, broken springs, clogged inlet and outlet. And with the valves, jammed stems, broken stems, ball jammed on the seat, ball jammed on other, and seat leakage. And over to the right, we have some representative failure rates that are somewhat familiar based on studies that we've done in the past. Now, with respect to where are you actually going to get the real data, well, number one, if you have it yourself due to your own maintenance work histories, that would be spectacular. But I highly doubt that even if you had good failure rate data, that you would have it at this level of detail. Hopefully, ultimately, we're all going to get there, but right now, I don't see it very often. In reality, the best resource for this type of data is going to be ORIDA, the Offshore Reliability Database. And that reference source probably gives more detail on the different failure modes than any other resource. So if you have a particular application that you're looking at, I would go to the ORIDA database first, get a copy of the book. All you need is the one page for whatever type of valve you're looking at, and use that as your resource to get these numbers over here on the right. Now, after you've put in all of the failure modes, you can look at the different types of, basically you assign them to safe and dangerous. We talked about all these. And if you look, there are very few failure modes on a valve system that are actually safe. I mean, there are very few things that will actually cause a valve to spontaneously move. The much more likely thing is that you command the valve to close and it doesn't. So of all of the dangerous failure modes, and to be honest, with a partial stroke test, you're only worried about dangerous coverage. Safe coverage doesn't help you. You're only worried about dangerous coverage. So for each one of those, you need to make the consideration, is a partial stroke test going to detect this? So for a, if the SOV coil is shorted, is a partial stroke test going to detect this? Depending on the type of test, the answer is usually yes, unless you're using something like a smart positioner to do the test and not including cycling the SOV as part of that test. Usually, you're going to do this, especially if the means by which you accomplish your partial stroke test is a command to de-energize the SOV. So that is, I'm going to say, is detectable. A stuck plunger in the SOV, for the same reasons, it should be detectable. If essentially, if you command the SOV, de-energize the SOV, and the valve, the SOV plunger is stuck, the valve isn't going to move, and your partial stroke test will fail. Okay. Similarly, for a jammed cylinder on the actuator, that should be testable. Broken spring in the actuator, that should be testable. And clogged inlets and outlets. So basically, everything in the SOV and everything in the actuator should be detectable with a partial stroke test. Now, what is not detectable all happens at the valve itself. Now, if the stem is jammed, your partial stroke test is not going to result in movement. So that's going to be detectable. But if the stem is broken, that is not going to be detectable. Your partial stroke test, let me step back a little bit. Your partial stroke test may succeed. If you have a very simple test that just checks for movement, you're not going to detect a broken stem. But if you're using a very elaborate, something like a smart positioner that's actually drawing a trend of the actuator pressure versus valve stroke, you will be able to detect a broken stem also. Next up, ball jammed on the seat. That's the big ticket one. That's the one that we're actually looking for most of the time. That is detected. But if the ball is jammed on something else, like a welding rod stuck in the pipe, or even some buildup of foreign material on or near the ball or where the valve closes, that may not be detectable. So what we do is, since it may or may not be detectable, we use a pessimistic option and say that it's not going to be detectable. Seat leakage is not detectable by a partial stroke test. It's not even detectable by a full stroke test. So if that valve strokes in the position or starts to move, your test is going to say that it's successful. But if there's a lot of corrosion that's eaten up the ball, it's not going to be able to actually block flow. So we would say that that failure mode is not detectable. Summing everything up on the next slide here, we had an overall failure rate, and then we split that failure rate into the safe and dangerous components. So of the dangerous components, we had 3515 fits. And of that 3515, we determined that 2930 of those are detectable. So we divide 2930 by 3515, and that gives us a diagnostic coverage of 83%. So that is the methodology. If you wanted to provide a very rigorous analysis to justify the number that you're going to put into your calculations for coverage provided by partial stroke testing, this is the methodology that we recommend to use it, to do that. The the data that you would use for this analysis is going to be sparse. The only reference that I could really point you to is going to be ORETA, which might not exactly match your application, so just use a bit of conservatism and a bit of judgment to come up with numbers for what you're going to do. And then you could take that number and plug it into the calculations that are in the ISA technical report that are in Paul Gruhn's book that you received with the class, and you should be able to go from there. That being said, that concludes the formal presentation here. I see that a few of the people arrived a little bit late, and what I mentioned at the beginning of the presentation is that we have a fairly small group here to where I went ahead and unmuted everyone. I believe, let me double check, but I believe I unmuted everyone. So if anyone has any questions, please feel free to ask away. 70% is very reasonable. We use numbers ranging from 60 to 85, depending on what the service is. And kind of what our going in position is that if it's kind of a service where the material in the pipe is kind of chunky or acidic or erosive, we'll start with 60%.
Yeah.
And then if we're talking about something clean, like if you're buying natural gas from the city for your fired heaters, that's going to be, 70 is an easy target to achieve there. Sure. You might even want to go higher than that. But if we put in anything higher than 70%, I'm going to put together this type of spreadsheet that I just showed you. Just something to stick in the file to justify that number that might seem a little bit aggressive when compared to some of the more conservative rules of thumb. So thanks again, everyone. I really appreciate your attention. And as I mentioned before during the training class, if you have any questions at all, don't be shy. Feel free to contact me. Email, voicemail. I'll probably pick up the phone and we can just talk. So thanks again, and let me know if you have any other questions.